Okay, welcome back. This is the second lecture. And okay, well, this is quite quick because in 1 week you need to learn lots of stuff. I don't know if it's very realistic, but this is what it is. But I want to encourage you to interrupt me whenever you feel like. And then if I don't finish what I wanted to do, it's not a big deal, okay? So please feel free to interrupt me. Do you hear okay, Giovanni? Okay. To interrupt me whenever, okay, if you have questions. Well, this morning, the only thing I really did was to give the definition of what is a Poisson structure and to give some examples, okay? Tomorrow in the class, in the problem sessions, you will work out more examples. I have a message from Jeff. I have a list of things I have to do this afternoon. So this is stressing me a little bit. Jeff is giving me an assignment. So here I have Poisson map, Hamiltonian vector field, Poisson vector field, symplectic foliation, Poisson submanifold, Scout and bracket, Bison bread. I'll do my best. OK, so with all this, you can do problems from 1 to 9. The list has 14 problems, so you can do the 9 first problems tonight, for instance. The problems will be copied and will arrive at some point, maybe during my lecture or maybe after my lecture. OK, having said that, let's start. I'm going to talk about local coordinates and how do we compute Poisson structures in a practical way now. So I'm going to take a coordinate system okay, and I'm going to denote omega ij, the Poisson bracket of the coordinate functions. Okay? Then I'm going to observe that these are functions again on my manifold, and I'm going to observe what are the properties of these functions. Okay? So we are assuming we have a coordinate system on a Poisson manifold, which so far I have been designing with this sign. In the next thing I will do is to talk about bivector fields just after this. So be ready for that. And the first properties of these functions are the following. First one is that these functions are antisymmetry. So have antisymmetry. The omega ij's equals minus omega ji. And the second property one observes is that since I know that Jacobi identity holds, I can do the following. Because of Jacobi, which is telling me, I apply Jacobi. Remember Jacobi, the property that we saw for any given triple of functions is this identity, okay? Now I'm going to plug here the coordinate functions, and what do I get? Jacobi gives me, making the identification already with the omega ij, this gives me the following expression. Xk plus omega jk plus omega k omega ki xj equal to 0. And I can even develop this expression further by remembering that I have the Leibniz condition, and Leibniz is telling me that this can be written exactly in the following way. I'm going to sum over L from L to 1 to n, the dimension of my manifold, and I have this expression. And here the order I have is partial of omega ij with respect to xl. This has to equal 0 for all combinations of a, j, k. Okay, so this is a set of equations that I have associated to the Jacobi condition. Okay, so the observation is, if I have a Poisson structure, then if I look at this Poisson structure in some local coordinate system, I get a set of functions which are anti-symmetric and satisfy this equation. And this equation is important. I'm going to label it with an asterisk. Okay, maybe 3. Because now assume, now how do I compute the bracket of any given functions from this condition? The bracket of any given functions can be computed very easily. If I call omega a matrix formed by these functions, then I can write this in a matricial form, like the differential of F transpose, omega, the differential of G. Okay, so I have a way to compute locally Jacobi brackets. And from this formula, well, this formula, where does it come? This formula comes from applying Leibniz rule in an iterative way, okay? And using this definition of the omega ij's, okay? So this is important because in the list of exercises that you have to do, from 1 to 9, this is a lot of things, sometimes you need to check that, that a given expression defines a Poisson bracket, and always the difficult thing is to check that satisfies the Jacobi identity. So if you have a structure that satisfies Leibniz, okay, and satisfies that it's anti-symmetric, then it's enough to check it on a basis. So it's enough to check this kind of expression. So it's enough, for instance, in this exercise, which is exercise 14, I think it's exercise it's exercise 12 in the current list we have, in which you have this determinant. A good way to solve it is just to do it in local coordinates and do it in a basis, okay? In a local coordinate chart. So now one can think of the converse thing. So conversely, given a skew-symmetric matrix omega ij, okay, then the formula fj, which is going to be ij from 1 to n, omega ij partial of f with respect to xi, partial of g with respect to xj, okay? Then this formula defines a Poisson bracket if condition 2, if omega ij satisfy equation three asterisk. So this is the way we are going to deal with Poisson brackets in practice, okay? Sometimes we need to take a coordinate system and verify that this condition is fulfilled. Okay, okay, there is another way. Well, I mean, how to see that this determines a Poisson structure. If you have this formula, this is a, sorry, this is f and j. If you have this formula here, it's easy to see that it satisfies it satisfies Leibniz. Okay, and then the Jacobi is given by this formula there. Okay, so there is another way, which is important. Let me do a couple of special cases, remark or examples. Let's call it examples. Example 1, the case in which these functions, omega ij, are linear functions. So if they are linear functions, I can write them in the following way. Xk for these functions here indeed are constants. Okay? So now I take a linear Poisson structure, which is linear in a system of coordinates. I'm taking a precise system of coordinates. The problem of linearization is something I want to reach at the very end of today's talk. But now I'm taking a particular system of coordinates in which my Poisson structure is linear. Observe the following. There is a connection between these coefficients of the linear function and some structural constants of a Lie algebra. So the condition, if I look at this expression on Rn now, if I look at this local coordinate system like a global thing, so I look at this in a vector space, okay, then the condition that thisCijk, so thisCijk, these coefficients, the omega ij are exactly these coefficients here, satisfy equation 3 asterisk is equivalent to the fact that these are indeed satisfy Jacobi. And I can take a basis of Rn. Okay, well, I can take a basis of a subalgebra of Rn, okay, such that these are the structural constants of this Lie algebra. Okay, so indeed, this is the same as saying thatCijk are the structural constants of a Lie subalgebra of my manifold of Rn. Indeed, I can think of the dual of Rn. This morning I didn't have time to explain the Poisson structure of the dual of the Lie algebra, which appeared in David's talk. And I'm going to defer to tomorrow's class to look at this example, because otherwise it's going to take me forever. And this is exercise 4 in the list. And another example, example 2, the case in which these functions are really constant. Then in this case, what I get is a Poisson structure, okay? If these functions are constant, a special case of this, we saw it this morning, the symplectic case would be the case in which these are example exactly 1, okay, in the Darboux coordinates. Then in this case, I get a Poisson structure, which is called regular, okay? Why? Because if I look at this omega ij like a tensor on my manifold, okay, it has constant rank. So in this case, we get, this is the case of regular Poisson structures. And this had been already studied by Lie himself. Okay? Okay, now I want to jump section 2.2 is going to be about another way to look at Poisson structures using bivector fields, which is the one which is more used. So section 2.2, The title is The Language of Bivector Fields. Okay? I'm going to look back into example 1 this morning, which is the example of symplectic forms. So I have a symplectic structure. Here I have the symplectic world. And I know the way to work with symplectic, in symplectic geometry is using forms. And this form, the form defining the symplectic structure, indeed is a closed form. And it's non-degenerate. But the language is using forms, the round forms. Okay? Now I'm going to go to Poisson, to the Poisson world. Okay? And here I take the way we know it so far, is we have these bilinear operations satisfying the 3 properties. Okay? And now I want to work in practice with this. And the truth is that I cannot work with forms. Okay? I need to think, indeed, like we saw in the last example this morning, the one of B symplectic structures, the one that I was looking on the sphere. Okay? What I have is a collection of symplectic manifolds. So I have to find a language that represents very well a collection of symplectic manifolds. And this is the language of bivector fields. So here I'm going to replace the language of forms by the language of bivector fields. Okay, what is a bivector field? Okay, a bivector field, to say it's short, is a section of the 2 exterior power of the tangent bundle. Okay, I say this, and I don't know if somebody is there. Okay, so I take a bivector field. This is a section of the 2 exterior power of the tangent bundle of M, okay, in local coordinates. This bivector field, I can write it. So bivector fields is a sophistication or a step forward after vector fields. Vector fields would be derivations, and observe that if I have a Poisson structure, then I have a kind of biderivation, because Leibniz formula is this is what it's telling me. Therefore, instead of using vector fields, I'm going to use bivector fields. Okay, bivector fields is a way to express a biderivation, indeed. And in local coordinates, this can be written like that. Okay, so I'm going to change the language of forms by a kind of dual language, okay, which is not completely dual because we cannot globally dualize, okay, but yes, on a basis, with the language, with combinations of expressions of this type, okay, which are really sections of this fiber bundle. Okay, I don't know. I'm not giving a lot of details here, but I want to be really practical. And so now I'm going to put a proposition which tells me that if I have a Poisson structure, this is what we have been seeing in coordinates, I can always associate a bivector field to it. Okay? So proposition 1. Given a Poisson structure, there exists a bivector field such that I can write for any pairs of functions, I can write this as the bivector field applied to the differential of f and differential of g. Why is this true? Okay, this is true because of if I have a Poisson structure, then observe that from the local coordinate systems, that the computations that we did, observe that at every point, the Poisson structures just depend on the differential of f and the differential of g at a point. This together with the fact that a Poisson structure is R bilinear implies that I can always find this pi. And if I want to put my hands into computations, how do I reconstruct this pi? Locally, the coefficients pi ij. So how do I reconstruct pi? The coefficients pi ij coincide exactly with omega ij. So exactly with the brackets, the Poisson brackets on a coordinate system. Okay, this is proposition 1. And proposition 2 is I want to see if there is a one-to-one correspondence between Poisson structures and bivector fields. Something is telling me that this is not so easy, because bivector fields is something which has very good properties. It's a kind of a fine thing. And I understood this morning that a Poisson structure is more complicated. I have some equation that needs to be integrated. So if I have a bivector field, okay, and I want to associate a Poisson structure, the recipe to do so would be this one. Okay, so proposition 2. The formula given a bivector field pi, the formula fj associated to pi defined as pi df which dj satisfies the following properties. First, is R bilinear, 1. Is antisymmetric, this is trivial. And 3, it satisfies Leibniz. Why does it satisfy Leibniz? Because observe that since pi is a biderivation, okay, then when I do the observation is that when I consider the Hamiltonian vector fields, what should be the Hamiltonian vector fields, which is something I need to define in general, if I consider this expression here, then this guy, by definition of what is a bivector field, this guy is a derivation. And this implies Leibniz formula. What about the Jacobi identity? Jacobi identity is an additional condition which in general is not automatically satisfied. For instance, let me give an example of bivector field that doesn't satisfy Jacobi. Let's do some computations. Okay, example. So the question is, does this formula satisfy Jacobi? And the answer is not in general. Let me put an example where this fails. I take the bivector field I take this bivector field And now I'm going to see if Jacobi works or not. Okay? So observe that I can recover the Poisson brackets from this bivector by observing that I have this equality, okay? That the coefficients are exactly the brackets. Okay, so this gives me the following. This gives me okay, just from this definition. And now Jacobi applied to the triple x, y, z. If Jacobi was satisfied, then I would have this identity. I want to see if this is 0. Okay? And the thing is that xy, it's 1. This is a derivation. Therefore, the derivation of constants, this is 0. Goodbye. What else do I have? I have that yz doesn't appear here. Therefore, yz is 0. OK? So goodbye. This is 0. And then this expression set x, this is minus x by antisymmetry. OK? And this expression xy, it's 1. Therefore, minus x y, it's minus 1. So this is different from 0. So this is an example of bivector field that doesn't satisfy Jacobi. Okay. Is there a way to write the Jacobi identity for bivector fields? There is a way to do it. And so I'm going, therefore, to complete. So not any bivector field gives me a Poisson structure. I need an additional condition. I'm writing something that I didn't define. So this is what is called the Schouten bracket. I need an additional condition, Schouten bracket. I plan to give the formal definition of this on lecture 3. But here, let me look again at my list of assignments. Jeff, Schouten bracket. It's in the last one. So what I'm going to do is to conceal what I want to do and what Jeff wants me to do. I'm going to give a computation kit for Schouten brackets of bivector fields. So I'm going to give 2 properties of Schouten brackets without defining them that should be enough to compute bivector fields. So tomorrow you'll be able to compute it. And then on Wednesday, since I will talk about Poisson cohomology, I'm going to give all the definition, all the properties, and so on. I'll try to use the projector. Otherwise, I will die on the blackboard. OK, so let me very quickly, this is a subsection that I want to dedicate to Jeff Scott, which is called Schouten bracket computation kit. So I'm going to do is, essentially, the Schouten bracket is an extension of the Lie bracket that works for vector fields to any multi-vector fields, in particular for bivector fields. And the way to define it, a way to do it is take some coordinates, define it in coordinates, and verify it satisfies a list of properties, which were studied by Schouten himself in his paper. And these lists of properties are the ones that are good to compute. So I'm going to list, there is a long list of properties. I'm going to give you 2 properties that you need to compute. Okay? The first thing that you need to know is that this Schouten bracket is going to be R-bilinear. Okay? So you can, if you have a combination of bivector fields, then you can take out sums and constants. You cannot take out functions. Then to deal with functions, you need to know the following. So if I have A, now the notation is going to be a bit cumbersome. A is a multi-vector field. So this is a section of of degree p, I'm going to say, of the tangent bundle of M. And B is a multivector field of degree q of the tangent bundle of M. Then there is a formula which is called graded anticommutativity, which is the fact that AB equals to minus 1, P minus 1, Q minus 1, BA. Okay, this is the first property that you need of this computation kit. And the second one is graded Leibniz. Graded Leibniz is telling me that if I have three bivector fields, three multivector fields, in practice, if you have to compute Schouten brackets just of bivector fields, okay, this property allows to, if you have a bivector field and a vector field, to turn things into vector field bivector field. And the second property allows me to reduce to the computation of Lie brackets. That's the idea. Okay? So this is something which reads in the following way. Okay, so for us, if you want to compute things which only imply bivector fields, the P's and the Q's are either 2 or 1. Okay? So the right thing to do now would be to give an example, but I'm going to leave it as an exercise. I'm going to leave as an exercise, use the computation kit to prove pi equals 0 for pi. I'm going to put an easy one. Let me see, I have here some easy computations. This one, for instance, yeah. Okay. You'll do thousands of them, or maybe 9 of them, tomorrow during the problem session. And Jeff will be here sweating. Okay, are you happy with that? That's good. Okay, let's go on. So this is, I mean, so far what I have been doing this afternoon looks a bit boring, but it's computations in coordinates. And now I want to do something more exciting. This is section 2.3, and it's called the Poisson category. But it's very simple. It just has a couple of definitions. Already this morning in the talk of David LeBlanc, we saw that the very definition of momentum map, he said a momentum map is a Poisson morphism. So he used the expression Poisson morphism between M and the dual of a Lie algebra. What is a Poisson morphism? Definition. So if I have two Poisson structures, now I can use both notations. I can use this notation and the notation of bivector fields. And from now on, I'm going to abuse this change of notation all the time. Okay? So now if I take, if these are two Poisson manifolds, a mapping phi from the first to the second one, let's say M and N, is called a Poisson morphism. If, as David told us this morning, if this sends the one Poisson bracket to the other. The way to write it is if the pullback of the Poisson bracket on N equals the Poisson bracket of the pullbacks. With respect to the first one, for any couple of functions. Okay? So this is the property of Poisson morphism. Okay, it takes one Poisson structure to the other. Examples. Example that we saw this morning is the example of a moment map. F from M to the dual of the Lie algebra, a moment map. Okay? Where I have M is a Poisson structure. Okay? And then the dual of the Lie algebra has the Poisson structure of vector size 4. Okay? So a moment map is an example of Poisson morphism. Another example, also from the world of Lie algebras, is consider a Lie subalgebra. Okay, or more generally consider a Lie subalgebra, which is a particular case of Poisson morphism, a particular case of Lie algebra morphism in general. But if I consider an inclusion, then the dual, this is an inclusion of Lie algebras, then the dual, and this is very useful, is a Poisson map. An example 3 yeah. Well, but M here, okay, I'm taking any Poisson manifold, not a Lie algebra, not the dual of a Lie algebra. I'm taking a Poisson manifold. If I have the moment map, I mean, it would be the same if this is a Lie algebra. I agree. Is a special case. Yeah, exactly. This is a special case of one. You don't need an injection. You enough to have a, and this is, I'm going to give you the chalk afterwards because we are going to talk about these kind of things. You can take a morphism, okay, of algebras. But I'm putting the injection because this is very good. This is a good way to produce integrable systems. And I want to reach that point. So yeah, there is a more general case in which instead of an inclusion, I take a morphism of Lie algebras, and then I can do the dual, and probably you're going to start with this thing, right? That's good, more or less. Okay, we are coordinated, that's good. And example 3, which is indeed a definition that it's in the list, in my list of duties. It says Poisson submanifold. Okay, so this is the definition indeed of Poisson submanifold. Which is take take a manifold, take a submanifold N, take a submanifold with a Poisson structure, okay, and take the ambient manifold with another Poisson structure, okay. Then I consider the inclusion map, and I say, so this is indeed not an example. I'm lying. This is indeed a definition, but in particular is an example a posteriori of Poisson submanifolds. Okay, so I take a manifold with a Poisson structure and the ambient manifold with another Poisson structure. So I say that N is a Poisson submanifold. If the inclusion map is a Poisson morphism. So we have a category. We have the objects. We have the morphism. What are the infinitesimal transformations of this category? These are what we call the Poisson vector fields. So I'm going to define what is a Poisson vector field, and I'm going to characterize how to see if a vector field is a Poisson vector field. Okay, I'm going to change the. So next definition is that of Poisson manifold, of Poisson vector field. Okay, a vector field is Poisson. Now I'm going to use the notation of a vector field if and only if the Lie derivative of the bivector field is 0. Okay? And this is equivalent. Remark, it's easy to see that if I take the flow of this Poisson vector field, the flow for each time t where it's defined, it's a Poisson morphism. Is there a way to characterize what a Poisson vector field in terms of the bracket? Yeah, we can see very easily. Remark, this is remark 1, and remark 2. We can see very easily that this condition here equal to 0. This is equivalent to x behaving in the following way with respect to the fact that this derivation of the bracket is x of f j plus f xj. This is just a simple computation, okay, where I just, Jeff will do it tomorrow to do exercise 5, right? Okay, so I've defined what is this category. I've defined what are the morphisms. Okay, I define what are the sub-objects and what are the infinitesimal automorphisms of these guys. Okay, I'm going to consider in the set of Poisson vector fields, there is a special subclass which is very important, which is the class of Hamiltonian vector fields. So my punchline is to study I'm going to consider the set of Hamiltonian vector fields. Oh my God. And before the end of the class today, I want to talk about symplectic foliation, and I want to talk about splitting theorem. And I have 15 minutes to do all this. I took a special juice that it's sold there in front, which is called triple revitalizer, but still I feel like I need more energy to do this. It's a bit hot indeed here. OK, so what I'm saying now, it's another definition, which is very important, is that of Hamiltonian vector field in the context of Poisson manifolds. How do we define Hamiltonian vector fields? In the Poisson case, it's very simple. We can define it with both notations in the following way. If I take f a function, let m be a Poisson manifold. A Hamiltonian vector field is defined associated to a function is defined by the following formula. It's x sub f. It's very simple. I just fix the first coordinate as f, and I leave free the second one. If I use the definition, if I use the notation of bivector fields, if I work with bivector fields, observation, the notation of bivector fields, the Hamiltonian vector field, okay, is exactly pi applied to the differential of f. Okay? Properties of Hamiltonian vector fields. We know, for instance, in the symplectic case, that if I have a symplectic transformation, a symplectic vector field, the difference between symplectic vector fields and Hamiltonian vector fields in the symplectic case is measured by the Durand cohomology. Here, this is measured by another cohomology, which is called Poisson cohomology, which will come in the next lecture. Okay? For many manifolds, I mean, the difference between Hamiltonian and Poisson can be infinite dimensional in the Poisson case. So it's very interesting to look at examples. Today, I'm just giving definitions very, very quickly. But one should stay a while and look at examples, do the exercises, etc. OK, so properties of Hamiltonian vector fields. The first one, that I've said it already, is that a Hamiltonian vector field is a Poisson vector field. OK, one needs to check this equality. OK, now I replace here x by the Hamiltonian vector field of f. And it turns out that if I replace here properties x is a Poisson vector field. OK, I have to check. OK, I'm going to change the notation because I'm going to use two f's, and this is going to be too much. I'm going to put h and j. Okay, I have to check this equality here, but now I replace x with a Hamiltonian vector field. And let's see what I get. Replace x by xf, and observe that what I have on the left-hand side of this equation here is nothing by this expression. Okay, and now if I apply Jacobi identity, this gives me exactly what I want to prove. Because of Jacobi, this is fh, and this is exactly x sub fh. Okay? Because I have this property as I had in the symplectic case, just because of the definition I'm doing of Hamiltonian vector fields, this is true. Okay, if I have the bracket, observe that here, if I apply this to j, this is exactly the bracket of f and j. Okay? Therefore, this guy here just comes from Jacobi. And here I have jh, fj, And this is exactly X sub Fj. Okay, so it's a Poisson vector field. A Hamiltonian vector field is a Poisson vector field. And important property that also comes from the bracket. Well, antisymmetry, for instance, tells me that Hamiltonian vector field preserves energy also in the Poisson case. So really easy, property 2, x sub f of f equals 0. And this is just because this is ff. Okay, and I know that this is 0 because it's antisymmetric. Property 3, and this is a very important property, that if I consider the bracket of two Hamiltonian vector fields, this is x of f and g. I plan to do this. This is just, indeed, if you try to do it at home in your hotel tonight, this is Jacobi identity. But this is also in exercise 5. So since time passes very quickly, I'm going to leave it to Jeff in exchange. OK. So I look at the list. And the only thing I need to talk about, I wanted to do the proof of splitting theorem, is what is a symplectic foliation. OK, so now I'm going to consider the set of Hamiltonian vector fields in the remaining 10 minutes. This is going to be intense. So please put your seatbelts on. So this is the last section, and this is called symplectic foliations, splitting theorem, and no normal forms. I don't have time. So this is section 2-4. OK? I'm going to talk about symplectic foliations. And splitting theorem. OK. I'm going to consider the following set, which is the set of Hamiltonian vector fields. Have a Poisson structure. I consider the set of Hamiltonian vector fields. Property 3. OK, this is a distribution. What is a distribution? I plan to give details, but I'm going to be very quick here. A distribution is just an assignment at each point of a manifold of a subspace of the tangent space at that point. OK? So all of you have done differential geometry. You know that there is an important result due to Frobenius, which is Frobenius' theorem, which tells me that a regular distribution is integrable even only if it's involutive. OK? So Frobenius' theorem takes care of regular distributions, and an integrable distribution is a distribution that, for which I take subspaces of the tangent space, and I can integrate them. Okay? And then I get a collection of manifolds, and this is a regular foliation. Okay? So what I'm saying now very quickly is that there is a theorem, which is called Frobenius theorem, which tells me that if D is a regular involutive distribution, then it is integrable. Integrable in the sense that there exists for each point of the manifold, there exists for each point of the manifold a submanifold such that the tangent space at that point coincides exactly with the distribution at that point. Okay? If we want to deal with singular distributions, then the analogous to Frobenius' theorem is called Sussman, and who is the other one? Is Stefan, oh my God. So the equivalent in the singular case is Stefan Sussman. Which tells me that indeed involutivity in general is not sufficient condition. In the case in which this distribution doesn't have constant rank, so the manifold that should integrate it jumps a dimension, then the condition of Stefan Sussman is a condition that this distribution is invariant. That I have a family generating this distribution at this family C. And this family C is invariant, or D invariant by C. So I have a condition that now I would like to stop to put counterexamples. It's impossible. Time is very short. So D is invariant by C. So what I'm going to say now is that if I consider the distribution of Hamiltonian vector fields on a Poisson manifold, because of this remark, this distribution, okay, is involutive. Because if I take the two Hamiltonian vector fields and I do the bracket, this is the Hamiltonian vector field of the bracket. Okay? But not only this, it satisfies the conditions of Stefan Sussman. So what I'm putting here is a kind of black box, but it's true, which is the following. It's a proposition. I have 5 minutes. I can put a proposition and a theorem, and then this is all yours. So the proposition is that the distribution generated by the Hamiltonian vector fields satisfies the conditions of Stefan Sussman and therefore, there exists a foliation, singular foliation. Now I'm going to be very primitive, thinking of a foliation just as a partition of my manifold into submanifolds which are immersed, but I'm hiding something, which is that there has to be a local property for this foliation. If you want to look at the details, I'm going to put the notes online so you can look at the details. Okay? So there exists a foliation integrating D. And indeed, this foliation is symplectic. I'm hiding a lot of details here, but I'm doing what I can. And now I want to finish with a characterization of the important theorem. This morning I talked about Darboux theorem, which is the local normal form of a symplectic structure. Now I want to talk about, just in the 1 minute I have, local normal forms of Poisson structures. And the best result we have without additional conditions is the following theorem due to Weinstein, 83, which is the following. In a neighborhood it's time, of any point of a Poisson manifold, there exist local coordinates I have some coordinates that come in pairs, and then I have some coordinates which I'm going to call transversal. Here I'm going to put this up to 2K. and such that the Poisson structure can be written in the following way. We have a part which looks like the dual of a symplectic form. And then I have a part which is the transverse Poisson structure, which is phi ij, only depending on the z's. And which satisfies with the property that these functions vanish at the point. Okay, I'm going to spend some time in lecture 3. I'm going to change a little bit my schedule because I really want to talk more about this result. This is a very important result in Poisson geometry, and this is the only, in the more general setting, the only normal form result that we have. Okay? So with what I explained today, you have enough material to look at the exercises, look at examples of symplectic foliation. And on Wednesday, I want to comment a little bit more on that. I'm going to spend maybe 15 minutes more talking about Weinstein splitting theorem and normal forms. And then I'll talk a little bit about Poisson cohomology and the modular class. OK, I'm done.